Alrighty. Howdy, folks. The next thing that we'll look at is section 7.8. It's called Improper Integrals. So to motivate you about this particular section, I want to start off asking you a question like this. Look at that integral that I have. Is that process okay, how I approached it? Integral 0 to infinity x dx, integral x is x squared over 2 for sure. And then we are supposed to evaluate it at the lower and upper limits, right? 0 to infinity. And I plugged infinity as a upper limit of integration and got in infinity square over 2 minus 0 square over 2. And infinity square is clearly infinity. Infinity divided by a finite number like that is still infinity, minus 0. Anything wrong with that? Yeah. Most of us, we think, yeah, there's nothing wrong with it. And in fact, I told you my PhD is in mechanical engineering. So I have seen many of my engineering colleagues and friends solve a problem just like that, without batting even an eyelid. But the thing is, no. When it comes to mathematicians, they just do not like stuff like that at all. Especially if somebody were to hear me, they'll go, Sam, did you say plug infinity? And you said infinity square is infinity. And man, you need to be fired, they would say. So what's the problem? Why do mathematicians object to approach like this? Okay, or maybe I'll put it this way: infinity is not a number like you can plug in. So there is no such thing as plug infinity. When x equals infinity, there is no such thing as x being equal to infinity. Okay. Now, as a concept, yes, it is true that we can talk about, hey, x is increasing, man. As it keeps increasing like that, what does it become? What does it approach? Well, if it keeps increasing, we can say x approaches infinity. But you cannot say x equals infinity. That's where all this issue starts. So what would they rather you do? This is how they want you to approach this. They say, all right, that upper limit of integration is infinity, right? You say that, replace that infinity with a t, and then say, you're going to say limit as t approaches infinity. That is mathematically more accurate, okay? And the rest of it is the same. Well, you integrate and then take and you get limit of t square over 2. And now, if you say, hey, what is limit of t square over 2 as t approaches infinity? Yep, that is infinity. And like I said, that is mathematically accurate. Okay? And you do the above and a mathematician is happy. Provocative. What should we do? The rebels that we are. Are we rebels? So, how about this? I don't want to keep writing that stupid limit as t approaches infinity, t approaches infinity, keep on doing that stuff. Instead, this is perfectly all right. If we get to 0 to infinity, now at this stage we are quote unquote plugging infinity for x, right? Don't do that. Don't say plug infinity. Instead you say, well, I'll evaluate this expression as x approaches infinity. So treat that, wherever you want to say plug infinity, instead replace that with I'll evaluate the limit as x approaches infinity. If you make that small modification, no mathematician can say anything. That's perfectly fine. Okay, so that's what we will do from now on. Okay, so this is accurate as well. Now, if a definite integral contains either positive infinity or negative infinity as its limit of integration, the integral is said to be a type 1 improper integral. So we got to know some of these definitions, just because if not for any other reason, somebody might say, hey, do you know how to deal with type 1 improper integrals, man? And you don't want to be in a position, what the hell is that? Right? You just want to know, oh, okay, type 1 improper integral. Yep, this is what we do. Okay, so let me illustrate. Is this a type 1 improper integral? Apply the definition. What does the definition say? Oh, is it a definite integral? Yep, it is. Is one of the limits positive infinity or negative infinity? Yep, the top limit is infinity. That's a type 1 improper integral. Cool. How do we evaluate this? Just evaluate the integral, and when we need to apply the limits, limit infinity, the upper limit, just say it as, I'm going to evaluate limit as x approaches infinity. Make that small change. Everything is fine and dandy, right? So what is now the question is, what is limit of e to the negative x as x approaches infinity? So here we are having to apply the concept of limit that we learned in calculus 1. Any thoughts on what limit of e to the negative x would be as x approaches infinity? Well, how about this? What if you think of e to the negative x as 1 over e to the x? Right? We could do that, right? Now, as x approaches infinity, what happens to the denominator? E to the x is the denominator. What happens as x goes to infinity? X approaches infinity. E to the infinity is getting bigger and bigger and bigger. So 1 over a very large number approaches what? Approaches 0. Is pretty close to 0. And that's how we can say limit of e to the negative x as x approaches infinity is 0. And what is e to the 0? Any non-zero number raised to 0 is 1. So we get 0, negative 0, which is same as 0. 0 plus 1 is 1. Cool. What? Couple things I need to point out. Because this improper integral, type 1 improper integral, turned out to be a finite quantity. I mean, the answer that we got when we evaluated that one, we got a nice simple 1. So we say, oh, the integral converges, or integral is convergent. Either phrase is used. No, I didn't mention it. What is fascinating here is, notice, we are integrating all the way from 0 to infinity, meaning we are finding the area of a curve, area below the curve e to the negative x, all the way from 0 to infinity. And still, the area turned out to be a finite quantity. Isn't that fascinating? When you think about it. Another reason why I want you to appreciate that is, pretty soon we are going to get into what are called infinite series, where we would be adding infinite number of terms, right? 1 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and so on. So 1 over 1 plus 1 over 2 plus 1 over 2 square plus 1 over 3 square, 1 over 2 cube plus 1 over 2 to the 4, and so on. Infinite number of terms. And well, that's stupid, man. If you add infinite number of terms, that's going to be infinity. It's going to be very large. Not so fast. That actually turns out to be a nice finite quantity. Okay, so I'll show you all of that stuff. So type 1 improper integrals are very, very important, uh, especially when you go to higher level classes. Okay, excuse me. Now let's look at this guy. Is this a type 1 improper integral? Apply definition. What was the definition of a type 1? What should be? It must be a definite integral. Is this a definite integral? Yes. One of the limits of integration must be either positive infinity and negative infinity. Is that the case? Yep. The bottom, the lower limit of integration is negative infinity. Cool. Type 1 improper integral. What's the integral of 1 over 2 minus 3x? Negative 1/3 natural log of absolute value of 2 minus 3x, right? Now we need to evaluate. Again, do not say plug negative infinity. Say evaluate limit as x approaches negative infinity of the inside quantity. So what did I do? I plugged 0 for x. That's okay. You can say plug 0 as long as you do not say plug infinity, negative infinity or infinity. 0. So this is 2 minus 0, 1/3, negative 1/3 natural log of 2. And then we have minus negative 1/3 becomes plus 1/3 limit of this. Okay, what happens to this limit? Well, 2 minus 3 times a large negative number. Okay, that's going to be 3 times a negative large number. Just give yourself some a million just for simplicity. So 2 minus negative 3 million or 2 plus 3 million. Oh, so that's actually a pretty large positive number. So that means 2 minus 3x itself would be approaching infinity. Natural log of something that is approaching infinity. Natural log of a very large number is also a large number. Okay. So this quantity inside the square bracket is actually approaching infinity. Oh, that means the whole thing is infinity. All right. So what can we say? We can say that the integral is divergent, or the integral diverges, because when we evaluated this improper integral, we got an infinity as the answer. So that means we say the integral diverges. Cool. All right. Now, on the other hand, let's evaluate this one. Again, observe that this is a type 1 improper integral because it's a definite integral with both negative infinity and infinity as the limits of integration. And we get this. Evaluate limit as x approaches infinity, and limit also limit as x approaches negative infinity. Okay. What is limit as x approaches infinity of e to the negative x square? As x approaches infinity. Maybe I should ask you a question. What is negative 2 square equal to? Negative 2 square. How many of you said positive 4? Nope. If that's what you said, you're wrong. This is actually negative 4. What? Yep, trust me. Negative 2 square is actually negative of the quantity 2 square, which I'm sure you'll now agree is negative 4. But why don't you think of this way, man? Negative 2 the quantity square. No, it's not equal to. Negative 2 square, written the way I did, does not mean the quantity negative 2 should be squared. It's only 2 which is being squared, and we have a negative on the outside. Okay, now do you see the pertinence of that discussion? So x square itself, now think of it as a large number, positive number, is being squared. So you still get a large positive number. So e raised to negative a very large positive number, that goes to 0. Okay? Now, how about e to the negative x square as x approaches negative infinity? Okay, as x approaches negative infinity, what happens to x square itself? A negative large number is getting squared. So that's a positive number.
Sorry,
Negative,
I'm not sure.
Negative of a positive, negative e raised to negative large positive number. Again, that is also 0. That also approaches 0. So we will say this is 0 plus 0, which is equal to 0, and surely the integral converges. Okay, now the next thing is all right, sorry about the pausing. Let's get back. Okay, is this process okay? What? I thought we already... No, we didn't look at this problem. It's different from the one that we started with. Notice, we are saying integral 1 to 4 of 1 over x minus 2, right? What's the integral of 1 over x minus 2? Natural log of absolute value of x minus 2. And we are supposed to evaluate it in the limits 1 to 4, right? Can I plug 4 for x? Yeah, natural log of 4 minus absolute 4 minus 2, natural log of absolute value of 1 minus 2. 4 minus 2 is 2, so absolute value of 2 is positive 2. Natural log of 2 is what we end up with. 1 minus 2 is negative 1. Absolute value of negative 1 is positive 1. So we have natural log of 1. Natural log of 1 is 0. So we end up with natural log of 2, which is a nice finite quantity. Therefore, the integral converges. Can I say that? I'm asking as a question, right? Is this process okay? Did I goof anywhere? If you want, pause the video. Nope, everything looks just fine and dandy, man. No, man. What's the problem? Well, the problem is, look at the interval of integration, 1 to 4, right? Does that have to go through 2? Meaning, x equals 1 to x equals 4. So at some stage, as we are integrating, would x become equal to a number in between 1 and 4, which is 2? Is there a problem at x equals 2? Yeah, the integrand is undefined. 1 over 2 minus 2, 1 over 0. 1 over 0 is undefined. But the process I applied for integration completely ignored that fact and just proceeded as if nothing is wrong, right? So no, this process is not okay. I cannot ignore. Oh, this is according to apparently any sane person. What's the issue? The interval contains 2 where the integrand is undefined. So, another way to state the same thing is there is an infinite discontinuity at x equals 2, which is a part of the interval of integration. That x equals 2 is a part of the integration, right? Interval of integration. Definite integrals that have an infinite discontinuity are called type 2 improper integrals. Earlier, we looked at type 1 improper integrals, but these are type 2 improper integrals. Cool? Now, how do we handle such integrals? What I want to say is, man, that's infinity. We are dividing by 0 and, well, what happened when we had to deal with some function like this? F of x is sine x over x. Can I ask what is f of 0? You'll say, oh, wait a minute, man, let me plug in 0 for x. So sine 0 over 0, sine 0 is 0, 0 over 0 is, please do not say 1. Okay. 0 over 0, that's undefined. Okay. So we know that f of 0, when f of x is sine x over x, is clearly undefined. Do not even mince words to say that, as you say that. Now, did we just give up and say, yep, that's 0, and so forget about it, man? That's undefined. So no, we said, wait a minute. We know f of 0 is undefined, but what happens if we don't let x equal 0, but we simply let x approach 0? Right? Clearly, when x equals 0, this f of x is undefined. There is no doubt about it. But when x approaches 0, meaning gets closer and closer. In fact, the term mathematicians use is when x gets arbitrarily close to 0. What in the world do they mean by gets arbitrarily close to 0? What they simply mean is x gets as close to 0 as you want it to be. What? What do you mean I can let x get as close? Suppose x is, say, a thousandth of an inch. Would you perceive that as being close? Yeah, man, thousandth of an inch, that's so tiny. Okay, then think of x approaching, x taking on a value like a thousandth of an inch. But there may be somebody else who may say, no, that is pretty far away. I want it to get even a little closer. Okay, what about 10 to the negative 100? You know how small 10 to the negative 100 is? 0.9901. If x gets that close to 0, are you happy? Yeah, that is really close. Okay, so take x to be 10 to the negative 100 if you want. Right, is the idea. And so we let x approach 0, both from the left-hand side and from the right-hand side, and look at this. Look at the same sine x over x. And it turns out, when we do that, this function has a value of 1, which is what we learned to say in Cal 1, limit as x approaches 0 minus of f of x. And that happens to be 1. Similarly, if we let x approach 0 from the right-hand side, 0 plus, again, that limit is 1. So this concept of using limit helped us when f of 0 itself was undefined by changing this to what happens if we simply let x approach 0. In type 2 improper integrals, that is the concept we'll apply. We do the following. If f has an infinite discontinuity at the upper limit of integration, okay, let's say we needed to evaluate, this is a type 2 improper integral, and at b there is an infinite discontinuity. Then we'll say, you know what? Our interval is a to b, right? And there is a problem at the upper limit be, I won't let x get to b. I won't let reach b, because if I let x reach b, then there is an issue. So what if I just stay slightly to the left of b, right? So what is staying slightly to the left of b mean? In limit terms, we will let x approach b minus. So we will replace the b with a b minus here in this context, because at b itself there is an issue. And we will evaluate this as a limit as x approaches b minus. In this case, we have to say limit as t approaches b minus, use a dummy variable t. I cannot say limit as x approaches b minus and say a to x f of x dx. That is wrong. Okay, you should not be, let me put it this way. Your limit of integration cannot contain an x if you are integrating with respect to x. That's a no-no. Let me repeat that. Your limit of integration cannot contain an x if you are integrating with respect to x. So you need to change this thing to, like the way we wrote, integral a to t f of x dx. That's okay. Or we could change it to a to x f of t dt, some other dummy variable t we can use. That's okay. All right, keep that in mind. Anyway, so how do we deal with situations of this kind? By doing this. Now, on the other hand, if we were to have an issue, an infinite discontinuity at the lower limit of integration, okay, which means at a there is a problem. Any thoughts on how to handle it? Hey, what if we don't let x equal a, but x simply stays to the right of a, right? So that means limit as x approaches a plus is how we will deal with this situation, right? That's it. Limit as t approaches a plus, integral t to b f of x dx. Mathematically, this is how they say, but I typically say I'll replace, like if I were to, maybe I'll show you with some few examples. Is there an issue? Where? At the upper limit too. Oh, cool. So what do? Don't let x approach 2. Don't let x become equal to 2. Stay slightly to the left of it. That means change this to 1 to 2 minus. And now with our concept, after we evaluate this integral, the way we will evaluate this is we'll simply say, we won't say plug 2 minus. Okay, we won't say plug 2 minus. No, instead we'll say take limit as x approaches 2 minus and apply that. Take limit as x approaches 2 minus of this quantity. Cool? Now let's ask, what is natural log of absolute value of x minus 2 as x approaches 2 minus? What do I mean by x approaches 2 minus? That means x gets as close to 2 as possible, but is slightly to the left of 2. Can you think of a number which is slightly to the left of 2? 1.9 or 1.99? Okay, cool. So what happens to, let's see what happens to this quantity when x happens to be 1.99. 1.99 minus 2 is negative 0.1. Absolute value of negative 0.1, right? Absolute value of negative 0.1 is positive 0.1. Cool. Natural log of 0.01. Natural log of 0.01. In fact, that's because we said we took x to be 1.99. If we had taken x to be even closer, that is 1.9999999 like that, we are talking about natural log of 0.000001. What is that equal to? Well, it doesn't equal something, but it approaches something. So for that, we should look at the graph of natural log of x itself. What are we looking at? Please pay attention to this. What are we talking about? We're talking about a scenario where x gets closer and closer to 0. Not x, but absolute value of x minus 2, the argument of natural log. There's a phrase called, there's a term called argument of natural log, meaning if I say natural log of 5, then the argument of natural log is 5. Natural log of 8 means argument is 8, so on. Okay, so as the argument is getting closer and closer to 0 from the right, notice what's happening to the natural log. It's going down and down and down. So it's approaching negative infinity, right? So this actually, the first term, that limit actually goes to negative infinity in this case. Negative infinity minus this quantity itself. 1 minus 2 is negative 1. Absolute value of negative 1 is positive 1. Natural log of 1 is 0. So we have negative infinity minus 0, which is negative infinity. Oh, this integral evaluated gave us negative infinity. So we'll say the integral diverges. Okay, integral is divergent or integral diverges. That is the concept. Cool. Let's recap. So since the problem is at the upper limit, we won't let x reach the upper limit. We'll stay slightly to the left of it, which we indicate as integrating to 2 minus. And then we'll evaluate limit as x approaches 2 minus instead of plugging 2 minus for x. What's the situation here? Oh, there's a problem at the lower limit. And what is our understanding? We will say 1 plus. We won't let x approach 1. We'll let x equal 1. We'll stay slightly to the right of 1. And so we have 1 plus to 5. Evaluate this integral and apply this. So far as the lower limit is concerned, we will evaluate limit as x approaches 1 plus. That's how we will handle it. Square root of 5 minus 1 is square root of 4, which is 2. 2 times 2 is 4. 4 minus. Now let's focus our attention on this. X is approaching 1 plus, meaning pretty close to 1, but to the right of 1. Can you pick a number that is slightly to the right of 1? 1.01? Okay, 1.01 minus 1 is 0.1. 1.01 minus 1, 0.01. 0.01. Can you take the square root of 0.01? Yeah, I don't know what exactly that equals, but or do I? Isn't it 0.1? Yeah, it's 0.1. What am I talking about? So square root of 0.01 is 0.1. We don't care about the exact value, but what is important is when x gets closer and closer to 1 from the right, we can evaluate square root of x minus 1. Let me repeat that. Please pay attention to that. What that taking x to be 1.01 has demonstrated to us is, if we let x get closer and closer to 1 from the right, we can evaluate this quantity square root of x minus 1. What's the big deal about that, man? If you say, the big deal is, ask the same question if as x approaches 1 minus. Can we evaluate square root of x minus 1 as x approaches 1 from the left? Plug x equals 0.99. then the stuff inside the radical is negative 0.01. Can you take square root of a negative number? Of course, not as a complex number. In calculus, we'll stay real. So as a real number, does square root of negative 0.01 exist? No, it doesn't. So that is the issue. But here, excuse me, there is no issue at all. X is approaching 1 from the right, and this value itself is actually approaching 0 as x approaches 1 plus square root of x minus 1 is approaching 0, so 2 times 0, and we can say, yep, this is equal to 4. All right. So the integral is convergent. And yeah, let's look at this statement. The problem shows that sometimes even if the integrand has an infinite discontinuity, the integral is convergent. The previous one, when there was an infinite discontinuity, that one diverged. But integrals need not diverge. These kind of type 2 improper integrals could converge. Okay. All right, one last problem, I think. What if f has an infinite discontinuity at some point in between the interval? Not at lower limit a nor at upper limit b, but somewhere in between. Then we need to split this integral from a to c and c to b. We learned in Cal 1 that that's perfectly fine, right? So we will integrate like this. Okay, what's the big deal about that? Now would you agree that because there is an infinite discontinuity at c, this integral a to c has become like our first problem, meaning upper limit has an infinite discontinuity. So we will evaluate this integral from a to c minus. And this other integral, c to b1, we will evaluate it from c plus to b. So thus we have avoided the c itself. In one case, we stayed slightly to the left of c. In the other case, we stayed slightly to the right of c. And we evaluate. And here is the beauty. This is case 1 that we looked at. If one integral diverges, let us say, you don't even need to evaluate the second one. Automatically, the whole thing is divergent and you move on. You don't even say, hey, but what if, man? There is no what if. If one of them diverges, you can go to the bank and say, yep, that integral is, the whole integral is 0. Okay. Now I know. You might be thinking, hey, what if one integral diverged because it's positive infinity and the other integral diverged because it is negative infinity? So you have infinity minus infinity. Isn't that equal to 0, man? No, infinity minus infinity is not 0. Infinity minus infinity is undefined. And in fact, in this case, we will say the integral diverges. All right. Okay, that's it, folks.